questions?
Beep. We are covering one-to-one functions and inverse functions. So I will begin with a word of prayer. So, Dearly Father, we thank you again for this day. Thank you for this class, and just pray that you just be with us today. Help us to glorify you what we do, and just to encourage the students to just do their best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. So yeah, I need to talk to you guys about one-to-one function. All right. So what is a one-to-one function? A one-to-one function is as follows. Definition: f of A equals to f of B implies A is equal to B for all A comma B in the domain of f. So this is what a one-to-one function. A one-to-one function is one for which if you set the output of the functions equal, then the input has to match up. Let me try to draw a picture of this. So like example one, I'll just kind of give you a generic function. It could look something like this, for example. All right. And I'm actually starting with a non-example because it's almost more interesting to have a non-example. What is not a one-to-one function? Well, this is not a one-to-one function. So here I'm looking at y equals f of x. That's the blue curve. All right. And if you look at this, right, if we look at the horizontal line, which I'll do a green horizontal line here, like so, and you could do other ones, but here's just one, all right? Check it out. There's two different points, here and here, which intersect the graph, let's say at A and at B, right? So what are these points? Well, this point would be A comma f of A, and that point right there would be B comma f of B, right? Because that's what it means to be a point on the graph. And if that's a horizontal line, we have what? We have f of A is equal to f of B does not imply A equals to B, right? Because here you have f of A is equal to f of B, and yet A and B are clearly not the same x value, right? So this function is not one-to-one. And we have a name for what I'm doing right now. It's called the horizontal line test. So we'd say that f fails the horizontal line test. Right? So well, I think maybe then your next question would be, okay, so if this is what it means to fail the horizontal line test, right? In other words, there's a horizontal line which cuts through the graph in 2 points. What does it mean to pass the horizontal line test? Well, for a function to pass the horizontal line test, it has to be the case that no matter what horizontal line you look at, it intersects the graph in at most 1 point. So if my function's graph looks like, oh, let's say this, I'll do one of these finite deals like that, all right? Suppose that's my y equals f of x, okay? Then that function passes the horizontal line test because no matter what horizontal line I look at, right? How many points do you hit the, see, you just hit 1 point, 1 point, 1 point, 1 point, 1 point, never more than one. I mean, you can also hit no points up here or down here, right? That's fine. There you go, Mia. Now you can see. So here, f passes horizontal line test. So that says, thus, f is 1-to-1 function. All right. So if you're given a graph for a function, right? Well, if you're given a graph, you can ask one question first, which is it a function? We do what to check if it's a function? We check the vertical line test, right? So if it passes the vertical line test, it's a function. If in addition it passes the horizontal line test, it's a one-to-one function. Not every function is one-to-one, all right? As I just showed you in example 1 there. Let's do one where we can make the graph ourselves, okay? So like example 3, how about this? F of x equals to, oh, I don't know, 4 minus x squared. That's kind of a nice function. Is this function one-to-one? Can you graph this function? What is it? The parabola. Agreed. It's got x-intercepts of plus and minus 2, right? It goes to y-intercept of 4, so it's something like this, right? I mean, you don't need to be super careful for the graph, but that's what the graph looks like, give or take, right? And is this a one-to-one function? Well, no. Right? Because we can look at the horizontal line like this one, and as you can see, fails. Horizontal line test. F not 1, 2, 1. By the way, we also use that abbreviation 1 to 1 like that. Sometimes I'll spell it out 1 dash the word 2 dash 1. But any questions? So I'll tell you what a person in the other section said today after I did this example or something like it. They're like, wait a minute, so no even function is 1 to 1. I was like, oh, that's a really nice comment. So let me share it with you guys too. So remark, even function, not 1 to 1. Why is that? What is the definition of an even function that does what? F of minus x is equal to f of x, right? So you can think of x as being a, or you can think of minus x as being a and x being b, whatever. The point is there's two different inputs which give you the same output, right? So it's not 1 to 1. Or if you like the graph of an even function, like the one that's on example 3, it's symmetric about the y-axis, right? So it fails the horizontal line test. Any questions? Okay, so example 4. Let's let g of x equals to 4 minus x squared for x greater than or equal to 0. In other words, I'm saying the domain of g is 0 to infinity. Again, my question, as is my question in every one of these examples, is the function 1 to 1 as given or not? So what did I do here? It's the same formula, right? What's the difference? Yeah, x has to be what? Greater than or equal to 0. So what do we got then? Right. So the graph is, it's just half, right? It's like just the half. This is just half, right? It's half of the previous one. The same points, but only the positive ones, yeah? And the y-intercept at 4, 0. It's gonna be 0, 4. Is that 1 to 1? I believe so. See, because you passed the horizontal line test, right? So, yes. Passes horizontal line test. G is 1 to 1 function. So actually, there's a name for what I just did, and I'll just share it with you because I think it's worth knowing about. It's not something I usually test on, except possibly as like a bonus question at most. But the relation between example 3 and example 4 is that of restriction. So G actually, what it is, it's equal to F restricted to 0 to infinity. So it's the restriction of F to the set 0 to infinity. So if you start thinking about this, you might realize, oh, if my function's not 1-to-1, maybe I could make it 1-to-1 by just making the domain smaller as appropriate. I could get rid of the doubling of values by like suitably restricting the domain. But I don't push this issue too hard in here because this is a subtle thing to actually put this into practice. However, it does matter if you go on to like Math 128 and you study inverse trig functions. This matters to the issue of inverse trig functions because every inverse to a trigonometric function is actually the restriction. It's actually the inverse of a restriction to the function. It's what's more properly called a local inverse. But anyway, I'm getting ahead of the story a bit. In fact, I'm telling a story that we don't even test on in here, so let me stop. All right. So if we got a graph, we can just try the horizontal line test, right? But sometimes we don't have a graph, we don't want to make the graph, and yet we want to decide whether or not the function's 1-to-1. So in that case, we take an algebraic approach. So example 5, let's suppose we had f of x equal to 3x minus 8 over x plus 2. I want to decide, is this 1-to-1 show algebraically? Yes or no? And so what does that mean? Well, what I'm trying to say is we're not going to make a graph. We're just going to directly test the definition using algebra. And so what we start with then is the assumption that f of a is equal to f of b. So let's write that down. F of a equals to f of b. What would that assume? If we say f of a equals to f of b, we are presupposing for a and b in the domain, okay? What would that mean? There is a little bit of a string attached to that. So f of a equals to f of b. I am assuming a and b are both not equal to what? 0 is fine. 0 is not the problem child here. 8 is okay, but -2 is what we want to get rid of. -2 gives division by 0. So a and b to be in the domain means that they're not equal to -2. Okay, that's all. I don't even usually write that down. I'm just, okay, so suppose f of a is equal to f of b. Then that implies that 3a minus 8 over a plus 2 is equal to 3b minus 8 over b plus 2. See, I just took the formula for the function and wrote a or b respectively in the place of x, okay? Now I'm going to do algebra. So what do we do? First move, let's cross to multiply the equation, all right? So this tells us that b plus 2 times 3a minus 8 is equal to a plus 2 times 3b minus 8. And, okay, now multiply out. What you got? You got yourself a 3ab minus 8b plus 6a minus 16 is equal to 3ab minus 8a plus 6b minus 16. I'll get out of the way here. All I'm doing is I cross multiplied and now I'm distributing. I'm multiplying it out, foiling it if you like, if that means something to you. Now, oh, well, look at that. Look at this. We got this here, but we also got one here, right? What else? We got a minus 16 here, but we also got a minus 16 here. So those cancel. And that gives us minus 8b plus 6a is equal to minus 8a plus 6b. All right. Great. Now what? Combine like terms? Okay, so this gives us what? This gives us, looks like 14a is equal to 14b. Oh, hey, what do you know? What's 8 plus?
Oh, no, I see it.
Oh, okay. You worried me for a second there. So, voila, a equals b. So we have now shown by direct algebraic argument that if f of a is equal to f of b, then a equals to b. All right? Therefore what? So thus, f is 1, 2, 1 function. All right? Let's do another, yeah? Example 6. Let's suppose we have f of x is equal to, say, the cube root of 13x minus 7. All right, is this a one-to-one function? What do you guys think? I think we can all agree, I mean, you could graph it. You could graph this. You could graph this, but I think it's more fun to not graph it. Let's just do the algebra. Let's check if this is one-to-one. All right, so here we go. Suppose f of a is equal to f of b. So like if I have a problem on the next test that starts with like, the instructions to the problem are like, show the function is injective, parentheses, or not, by a direct algebraic argument, that direct algebraic argument must start with something like the words, suppose f of a is equal to f of b. That's how we start. We are assuming that the outputs are equal. That has to be the starting point. Anything other than that, I don't know what you're doing, but it wouldn't be good. So, well, that implies that the cube root of 13a minus 7 is equal to the cube root of 13b minus 7, right? But then I can take that and do what? How do I get rid of the natural enemy of the cube root? The cube, right? So we cube both sides. And that gives us 13a minus 7 is equal to 13b minus 7, which of course gives us 13a is equal to 13b, which gives us a is equal to b. Hooray! The function is one-to-one. All right, let me do something foolish. Let me try one I'm not sure I'm going to be able to work out the algebra for. All right, let's see how this goes. How about this? Let's see here. F of x equals to x to the 4th plus x squared plus 2. Let's see if we can show that this I mean, this is kind of dumb. Let me make it less dumb. Make that a 2x there. Now it's less dumb. See, if I didn't have that 2x there, it'd be even, you know? And I know that an even function is not one-to-one. Because I could just do stuff like, I could look at 1 and, by the way, to prove something's not one-to-one, all you have to do is find one counterexample. All right? Like if I can find two inputs that give me the same output, then I've shown it's not one-to-one. Yeah? So like, example 8, if I had f of x is equal to x to the 4th plus x to the 10th, I could see that that's not one-to-one, because if I look at f of 1, I get 1 plus 1, which is 2, right? And if I look at f of minus 1, what do I get? Minus 1 to the 4th, right? Plus minus 1 to the 10th, which is also equal to 2. So we have f of 1 equals to f of minus 1, yet 1 is not equal to minus 1. So, you know, thus f not one-to-one. All right? To prove something's not one-to-one, it actually suffices to give a counterexample. All right? Anyway, let's try the example 7. So I start with what? Unless you guys can tell me two different things to put into that function to get the same output, but I don't know if I can. Let's not try to guess that. So suppose f of a is equal to f of b, right? Then what do we have? We have a to the 4th plus a squared plus 2a is equal to b to the 4th plus b squared plus 2b. Yeah, I'm already regretting this example. So what can I do here? See, if I know a is equal to b, then it's easy to solve, right? But I don't know that, right? I'm trying to prove that. I don't know. I think at this point, I just have to admit defeat. Like I'm stuck. I can't go forward on this example. So I have to be careful which examples I give to you guys and ask you to show them algebraically. The formula has to be amenable to algebra that you guys know, like my previous examples, right? There are functions where the algebra is like a little bit too difficult for us to hack our way through. I don't think I can factor that nicely. I guess I could, right? This is, oh yeah. I can take out an a, but that doesn't help too much because then I'm I'm up against that. And I can take out a b, right? And that's lovely, you know. And then I could say, well, I can suppose a and b are non-zero and kind of investigate that. Let's stop. Let's just stop. Okay. So like this is an unfair question. So how would I solve that? Well, first of all, if that question was on a test, it would end up getting omitted. So you'd be like, yay, everyone gets credit, right? If it's in homework, though, you could just graph, right? You could look at a graph of this with Desmos or something. And then you could look at the graph. If the graph passes the horizontal line test, then great. If it doesn't, then not. What does the graph of this look like? That I actually think we can make progress on. What is the graph of y equals x to the 4th plus x squared plus 2x look like? Well, that's x times x cubed plus x plus 2, right? Now, I don't know about factoring this, right? I don't know about factoring this. I mean, we can't just factor an arbitrary cubic, can we? But what we could do is plug in a number. What happens if you plug in like, I don't know, minus 2? What do we get from here? Minus 8, minus 2, plus 2, also known as minus 8, right? What happens if you plug in, say, x equals to 2 into this? What's that? You get what? 8 plus 2 plus 2. We get 12. It's got a 0 where? Okay, so what that means, just looking at this cubic, there's some place it has a 0 between -2 and 2. Maybe I need to check. Let's try x equals to 1. What does that give us? Maybe try x equal to -1. X equal to -1 gives me -1 -1 plus 2, which is, oh, what? Dude, seriously? Why didn't you guys tell me that? You guys already knew that -1 was a 0 of this, didn't you? Someone here knew. It wasn't telling me. It was you? Okay. So this is actually x times x plus 1 times something. All right. There's an x squared here. And there's like a something here, and there's a 2 here. I don't want to figure out what the middle thing is. It doesn't really matter. That's prime. What's that? Long divided, yes. But we could do that, but I'm not going to at the moment. The point is that this has a 0 at 0 and also at -1. And that's it. Those are the only zeros, right? The only zeros of this quartic are at 0 and also at the single isolated real 0 of that. I'm relative. Well, actually, I don't know. Darn it. You were not wrong. I need to long divide that to be sure. Why have I done this? I didn't do this in the others. I had the good section. I had the good sense to not do this in the other section. Oh my goodness! I tell you what, x squared. You guys are so quiet. You make me nervous, and then I do hard stuff in here. X cubed plus x squared. We take the difference, and we get minus x squared plus x plus 2, and then minus x apparently. So that gives me minus x squared minus x. Take the difference, that gives me 2x plus 2, that's good, plus 2. Does this thing factor? Up here? Does that factor? So that's like this thing, b squared minus 4ac for this would be 1 minus 4 times 1 times 2, which is negative 0. So this is prime. Okay, fine. No, that needs a what? So I believe what we have altogether for the quartic is y is equal to x times x plus 1 times x squared minus x plus 2. And you think that factors? It's a plus 2. If it was a minus 2, I'd be on board. But it's a plus 2. It's a plus 2, not a you're thinking minus 2. The reason I know this doesn't factor is I just checked the discriminant up here, b squared minus 4ac for it. And so if here b is equal to 1, minus 1 rather, and a is 1 and c is 2, that gives me a negative 7 discriminant, which means that this is a prime quadratic, which means that's complete factorization, which means that the quartic only goes through 0 at minus 1 and 0. But it's also a quartic with a positive leading coefficient, which means it looks like one of these deals, which means the graph has to look something kind of sort of like this. Which means this function is not one-to-one because it fails the horizontal line test, right? All right, so example 8 is definitely like too hard, okay? I should have bailed on it like 10 minutes ago. My apologies. All right? Now, one more example of this nature, and then we'll be done with this part of the course. Not this part of the course, but this kind of example anyway. What if we had example 9? Oh, I'm sorry, that was example 7, wasn't it?
No, we're on example 9.
Yeah, I know, but my point was I was just talking about example 7, not example 8 over there. So example, you're right, we're on example 9. How about this? F of x equal to 3x squared plus 2, say. Is this function one-to-one? Well, of course, this one, you could just graph, admittedly, right? You could graph. But let's do the algebra thing, see what goes wrong. So we have f of a equals to f of b. That would imply 3a squared plus 2 equals to 3b squared plus 2. Then that tells me that 3a squared is equal to 3b squared, which tells me that a squared is equal to b squared dividing by 3, which tells me a is equal to plus or minus b. So thus, f not 1. What was the question?
Never mind. I asked you plus or minus a equals plus or minus b.
Yes, in principle, but the pluses and minuses are disconnected.
Yeah.
So logically, it calls back to just what I wrote. But yeah, you're absolutely right. In principle. And if the plus minus principle, taking the square root, I'm using the square root property there. Like if you don't like that, logically another way that if this bothers you, you could do this. A squared minus b squared equals to 0, which is the same as a plus b times a minus b equals to 0. And then by the 0 property, either you have a equals to minus b or a equals to b from this, which gets us back to that. So if you want to, you can see it that way. All right. So this is the one-to-one property. Why do we care? Like, who cares about one-to-one property anyway? Like, you know, what does it matter? Because what?
Only because you're going to ask about it.
Only because of the threat of my threat over your GPA?
Yeah.
No, well, that's kind of depressing, but no, there's another reason. And it is because we need the one-to-one property to meaningfully define the next thing, which is what we're actually interested in, which is the concept of an inverse function. Right? What's an inverse function? So let's define it. Uh-oh. Did I ever move the camera? Did I move it over to here?
No.
Oh, right.
Rats. I am.
Yeah, my desk got taken off from the camera.
Oh, sorry.
That's
I guess that'll do it.
okay. Sorry to those viewers.
Yeah, and people who aren't here, it's, you know. I should. You think I should? You know, I do need to invent some merch and such. I need to monetize this thing. Okay, so here's the deal. Let us talk about inverse functions. So I usually start with a picture. Here's a set A. Here's a set B. And my function goes from A to B, all right? And I want to assume that this is a one-to-one function. Then the inverse function goes the other way. All right? And so the basic setup is this. The domain of f is equal to a, and that's going to be equal to the range of my inverse function. On the other hand, the range of my function is going to be b, and that's going to be the domain of the inverse function. So the function and its inverse, they share the range and domain in an inverse kind of a dual fashion here. So here's the definition. Given f, a function from a to b, which is 1, 2, 1, and the range of f is actually equal to b, then f inverse from b to a is defined by y equals f of x whenever x is equal to f inverse of y. I mean, you could change the grammar up on that. Let me just write that backwards. Let me write it. X is equal to f inverse of y is equal to x whenever y is equal to f of x. And I like to just draw the x and the y in the picture to just kind of like visualize what's going on here. You know, x is here, all right? And then f moves x all the way over here to b, to this point we call y, and y is equal to f of x, right? Well, the inverse function takes this y and moves it back there. So f inverse of y is equal to x. Now, we can also write two equations which capture this whole idea, and I sometimes refer to these two equations as the definition. And here's the equations that the function and its inverse must satisfy. In particular, we must have that f inverse of f of x has to be equal to x, and we must have that f of f inverse of y is equal to y. The first equation has to hold for each x in the domain of f, and this has to happen for each y in the range of f. But we do have to have these two relations. And you notice why the one-to-one property is needed. Did you see that? If we were trying to define f inverse of y is equal to x, that has to be a single value, right? What would the problem be if y is equal to f of x for two different choices of x, right? If y was equal to f of x1 and y was equal to f of x2, where x1 is not equal to x2, I wouldn't know when I wrote this formula whether to put x1 or to put x2. But because the function is one-to-one, this is a single value. This defines a single value, all right? Now, let me show you guys the algorithm for how to find the formula for the inverse. So, you know, definitions are fun and everything, but what's you guys probably want to know is how do you actually find the inverse? Like what's a typical homework question about this stuff? Well, a typical homework question is, here's a formula, find the formula for the inverse, all right? So let's actually do that. Here's the algorithm, as I practice it anyway. Algorithm for finding the inverse function. Step number one. You're given one-to-one function, f of x, all right? Set y equals to f of x, all right? That's point number one. And just for the sake of reference, let's call that star. All right? Step number two. Solve star for x equals to stuff in y. All right? Hang with me here. Step number three. Write f inverse of y is equal to stuff in y. Congratulations, you just found the formula for the inverse. Hooray. That's all there is to it. Now, if in addition you want to find the formula for the inverse function in terms of x, there's an extra step. Step 4. If desired, swap y for x and write f inverse of x equals whatever that stuff was, but in x. All right, let's try it out. Let's try it out. So example 10. All right. Time flies when you're having fun here. Let's see here. So how about f of x equals to 3x minus 3. Can you guys find me the formula for the inverse function? I'll get us started. Y equals to 3x minus 3. Solve for x now, okay? Can you guys solve for x? Let's see here. So we've got 3x is equal to y plus 3, right? Now divide by 3. We've got x is equal to 1/3 of y plus 3, right? And that is what I meant by quote-unquote stuff in y. There's my stuff in y for this problem, right? So what's the formula? Here you go. F inverse of y is 1/3 y plus 3. And that's all there is to it. Now I guess I could ask a question, follow-up question here. Why would you do a step 4? Like, what reason would you want to do step 4 for? Yeah.
To find no, actually, it doesn't make any sense. Never.
No, it's fine. So if you think back to how you were taught math before, if you can remember that, right? You probably were taught to switch y and x at the start. Why was that? Well, here's the difference. Your previous instructor probably didn't want you to think about a function of y. I have a high opinion of you guys. I think you can think about a function of y. It's not a deal breaker. And it just simplifies the problem also if you don't have to have the swapping x and y step. Because in my experience, you guys will swap x and y at an arbitrary step in the middle somewhere, and then everything goes haywire. So I just prefer to do the 1, 2, 3 if I can get away with it. It makes the problem easier. But if you were going to graph functions, we usually want to graph a function of x. That's what we're kind of hardwired for. So let's look at example 10. Let's graph both the function and its inverse. So the inverse function of the function of x is very silly. Here it is. F inverse of x is equal to what? 1/3 x plus 3. See? Big deal. There it is. Let's graph, though. What's going on here? Here's my x. Here's my y. So how about the original function? You guys tell me. What's its graph look like? It's a line. What's the y-intercept? -3. All right. And its slope is what? 3. So it's something like that, up to the limits of my artistry here. There you got your y is equal to f of x, which is equal to 3x minus 3. And is this one perpendicular? I don't think it is, though. The other one, what's this one? It's 1/3 x, right? If we multiply the 3 times 1/3, we get plus 1, right? So the y-intercept of the inverse function, which is also a line, has a y-intercept of 1 and a slope of 1/3, right? And let's see here. So its graph looks something like this, right? There's y equals to f inverse of x, which in this case is 1/3 x plus 1. Can you guys explain to me how are these graphs related? Yep.
Like the points, like 3, 0 is just swap.
Oh. You're saying there's a swapping of points? I like that. I think there's two obvious things to look at, right? Like this point right here is 1, 0. That point right there is 0, 1. This y-intercept is 0, minus 3. This x-intercept over here is minus 3, 0, right? That's not an accident. There's a theorem, in fact. Here's the theorem. A comma b, all right, is an element of the graph of f only if b comma a is an element of the graph of f inverse. So that's a fancy way of saying that the graph of a function and the graph of the inverse function are symmetric about the line y equals x. So if I draw the line y equals x as green, there should be kind of like a mirror symmetry of the graph of the function and its inverse. They get reflected one over the other. If you look at perpendicular bisectors to the green dotted line, the distance from the graph of the function to its inverse should be the same if I did my picture exactly right. Like if I did this exactly right, this perpendicular bisector, this distance here and that distance there, they should be the same, which shows you my picture is not quite right, okay? But questions?
Will the line of symmetry always be like this?
Yes.
It will, okay.
Right. That's what this theorem says, that AB is, if you reflect A and B to B, and if you think about what this does, that is going over the line y equals x. Like,
It's perfectly mirroring it.
yeah,
Okay.
yeah. This always happens for an inverse function. Is it that time already? Oh man. Aw. I guess I probably should hand back the tests, huh? Oh, we're not done with this, by the way. The whole next class is all this, all right? So.